Is there life beyond Earth? Finding it is something that might happen in the next few years. The laws of nature, the basic fundamental laws of nature, don't care which way you run time. So if you throw the book into a black hole, is that information somehow imprinted in the Hawking radiation? When the black hole's gone, Stephen Hawking's calculation said no, information less. And the current consensus now is that the information comes out again.
Life beyond Earth, the secrets of black holes and 13.8 billion years of cosmic history. Professor Brian Cox joins our show This Is World to reveal where we're hunting for microbes today, why information from black holes isn't lost, and how quantum computers are set to transform physics.
Is there any question that nobody asks you, but you would like to answer?
It's a good question. I've probably been asked almost all of the questions in my time. I mean, the common ones are, I think the best questions are, how do we know? Because, right at the start of the live show, I will say things like the universe is 13.8 billion years old. There are something like 2 trillion galaxies in the observable universe. And also I make an argument about life in the universe, which is a guess, because there are quite a lot of things we don't know. So I think the best kind of questions are questions such as, well, how do you find out how old a universe is? I mean, I often say to the audience, if you think about it, if you pick up a rock from a beach, how do you know how old it is? It's difficult. It takes a lot. Basically, we have to know a lot of nuclear physics. We have to have a lot of equipment in order to work out how old something is that we hold in our hands. So how do you know? And so I think those are the best questions. And I answer some of them. There are 2 kinds of questions in science. There are the ones that you think you might get an answer to in your lifetime, and there are ones that you don't. So I think a very important question is there life beyond Earth? Now, of course, most people would say, well, there has to be, because the universe is so vast and so old and there are so many stars. But actually, finding it is something that might happen in the next few years, let's say the next decade or two, because we have space missions out there. We have a mission called Mars Sample Return, which is based on the Perseverance rover's samples that it has now collected on the surface of Mars. And we want to get them back to Earth to see if there's any traces that life may have existed or may still exist. There are 2 missions, one on the way and one about to launch to Jupiter's moon Europa, which are missions aimed at trying to find out whether that place is potentially a home for life. So I think the question, it's one of the big questions, are we alone in the universe? Of course, you can never say, yes, we're alone, but we might be able to say definitively, no, there is life beyond Earth in the next decade or so. I would say, by the way, that if we find life elsewhere in the solar system, it will be at best microbes. We're pretty sure of that.
In our galaxy?
The galaxy, I mean, in the show, I asked that question because it's an important one. How many civilizations are there in a typical galaxy? And of course, the answer is we don't know. However, we can make some guess. And so I make my own guess in the show, and I justify why I come to this conclusion. My conclusion is there might be very few intelligent civilizations in a galaxy. I asked a great friend of mine, actually, Sean Carroll, who you might know, the author and cosmologist, what do you think? On average, how many civilizations are there in a typical galaxy? And he said, none on the average.
But do you believe that we ever find bacteria in our galaxy?
I would not be surprised at all. And this is part of the live show. So I say, well, what do we know? What evidence do we have? How can we speculate about these things? Well, we know we have good evidence that life was present on Earth around 3.8 billion years ago, which is interesting in itself because that's pretty close to the age of the Earth. So on this planet, as soon as the Earth had formed 4.5 billion years ago, it cooled down, the oceans formed on the surface. Not so long after that, we have evidence that life was present. So that's the observation that we have. So that might suggest that if you have the right conditions, geological conditions, then I say that what kind of a thing is the origin of life? It's a transition from geochemistry to biochemistry. Whatever it is, you have a geologically active world and then you have a biologically active world. So given the right geology, perhaps it's not so unlikely that life begins. That's all. That's what you can say from the evidence on Earth. It could be we're very, very lucky on this planet, but let's say that given the right geology. So that the strategy for looking for life beyond Earth in the solar system is based on that idea that if you go to places where there was or still is liquid water, and you go to places where there's geological activity, and you go to places where the right chemistry we think exists. And so that would be Mars in the past, perhaps Jupiter's moon Europa now, perhaps Saturn's moon Enceladus now, perhaps other moons of Jupiter or Saturn. Then, so that's the strategy. You go to the places where the geology looks right and the chemistry looks right and look. And that's all we can do ultimately. So I wouldn't be surprised, to answer your question, if we find some kind of life on those moons or perhaps subsurface on Mars. I would be extremely surprised if it was complex life, by which I mean multicellular life. And that's based on the fact that we have no evidence of multicellular life on Earth back further than, let's say, 1 billion years at most, actually maybe 600 or 700 million. So the evidence from Earth is that life remains simple for something like 3 billion years. And that's why most biologists will say that whilst microbes might be common in the solar system, complex life, it would be very surprising indeed if we found that.
How do you define the term time?
It's an absolutely superb question. The answer is that this is a current area of research. We don't know what time is. So in Einstein's theory of relativity, which is our best theory of space and time, that we have a picture of space and time woven together into what's often called the fabric of the universe. It's called space-time. And there's a notion of distances on that surface. And they're measured by clocks. So a clock is measuring it. Let's say you have a perfect stopwatch that you start the moment you're born and you keep it with you for your whole life and you look at it now. Then that's measured your age. It's also, in Einstein's theory, measured the distance you have traveled over space-time during your life. That's fine, but it assumes there's such a thing as a clock, right? So the age of the universe, by the way, is defined as the time that would be measured on a freely falling clock that had started ticking at the Big Bang, and you had a look at it now. So a clock that just falls freely through the universe. So that's but it still doesn't say what time is. So you will see discussions in the textbooks and online about something called the thermodynamic arrow of time. So it is true to say that, for example, the laws of nature, the basic fundamental laws of nature, don't care which way you run time. So they'll run. So basically, if you know everything about some system at some point in time, then the laws of nature will allow you to run that forwards to see what it's going to be doing in the future, or they will allow you to run it backwards to see what it would be doing in the past. So it's completely symmetric. But of course, there is a notion of past, present, and future. It's complex, actually, in relativity to define what that is, but we feel it. We think the future is yet to come and the past has happened. So we do know that asymmetry has a great deal to do with the presence of this unusual thing in the past called the Big Bang, which was very highly ordered. It's got, technically, you say it's a low entropy. And we have this idea of there's a thing called the second law of thermodynamics, which tells us that entropy always increases. And so the future is in the direction of entropy increasing, right? So things getting more disordered. So that's an idea of time. It's called the thermodynamic arrow of time. But when you get into what a clock is, and what it's measuring. You could go now online and you'll find a lot of research papers, where the interesting fields of research, such as what's the minimum clock you can make. You'll find actually that there are papers. I read one last week, which was a clock made of three atoms, basically, and the ticking of the clock is associated with light being emitted from the atoms as electrons jump around in the energy levels. You do need what's called a hot reservoir and a cold reservoir for that to work. So a clock is a thermodynamic machine. It's like a steam engine, right? So one way of thinking about clocks is that they measure the flow of entropy and so on. So the reason I say all this is it's quite technical language. I mean, it's well defined as the time measured on a clock that's been freely flowing through the universe. I mean, another way to look at this question, though, is we say how old the universe is. The measurement we have is the time on that clock from the Big Bang to now, which is the time from when the universe was hot and dense to the present day. Now, our best theory of how the universe came to be the way that it is a theory called inflation, which has space-time being present before the universe was hot and dense. So before the Big Bang, in that sense, we call the Big Bang the hot Big Bang now for that reason. And then you get into questions about, well, what does it mean for the universe to have a beginning? For that, we need to understand what time is. And there are other theories, so-called quantum theories of gravity, which are being developed now, particularly actually in response to research into black holes, which are suggesting that space and time themselves emerge from a deeper theory that doesn't have space and time in it. These are theories called emergent space-time theories. And so you need to know, ultimately, my view is we need to know what space and time are before we can talk with confidence, even begin to answer the question, did the universe have an origin? Because we don't actually know what a beginning is in a universe without space and time. So, yeah, so, these are great questions.
Do you believe that we can see the light that has been traveling to us from before Big Bang?
No, so the oldest light in the universe, we know we've captured that. It's called the cosmic microwave background radiation. So that was emitted 380,000 years after the Big Bang. We know that because before that time, the universe was so hot that it was in what's called a plasma state. So it's primarily hydrogen and helium gas. But if you go back beyond 380,000 years, so earlier than that, then the universe was so hot that atoms couldn't form. So you have basically hydrogen and helium nuclei and electrons all over the place in like a soup. And that's opaque to light. Light can't travel through it. So you can't use light to see further back in time than 380,000 years after the Big Bang. But we have a beautiful photograph of that light. By the most recent is taken by a satellite called Planck, and it's a remarkable image, and it's an image of the universe as it was at that time. But further back than that, you need to do something else. You need to use the neutrinos or gravitational waves potentially. So our universe is expanding, and that's a discovery that was actually, believe it or not quite a prediction, but it was thought to be likely shortly after Einstein's theory of gravity was published in 1915. So the idea that the universe can stretch or shrink, the fabric, imagine space stretching or shrinking, was noticed theoretically. And then in the late 1920s, Edwin Hubble, the American astronomer, demonstrated that indeed, if you look at distant galaxies, they're all moving away from each other and from us. And through those measurements, that's essentially what we feed into Einstein's theory to calculate the age of the universe. So we can measure how it's expanded and how that expansion rate changes over time. So that's been known since the 1920s. So the universe is expanding and cooling, and that's the way that it is. It's actually accelerating in its expansion.
Do you believe that the Rosen-Einstein bridges or wormholes let us ever traveling around the galaxies?
Well, so it's an interesting question again. So the idea, by the way, the Einstein-Rosen bridge wormhole, that comes from a paper in the mid 1930s from Einstein and Rosen, and it's a property of the space-time, which a man called Carl Schwarzschild discovered actually way back in 1916. And it's if you have an eternal black hole, an eternal universe, so a black hole that's always existed, then you have this mathematical solution, which is a black hole and a white hole and a wormhole connecting them. It turns out you can't go through it because of the way the wormhole evolves as you fall in. And so, but you can imagine those geometries, those so-called wormhole geometries in relativity. Now you need, in order to construct stable ones that you could travel through, you need forms of energy or matter that we don't think exist in the universe. So you can read this. It's a great book actually from a long time ago by Kip Thorne on this called I think it's called Black Holes, Time Warps and Time Machines or something like that. I can't remember. It's a great book by Kip, and in there you'll see a discussion. And so the guess, it's not been proved right beyond doubt, but the guess is that it is nature will not produce stable wormholes that you can travel through as an astronaut or with a spaceship or so on. So that's where we are at the moment. There are good reasons for thinking that whilst they can exist theoretically, then stable ones that you could go through will not exist. But it's not been proved conclusively from first principles. I should say that there are different kinds of wormholes. So in the study of black holes at the moment, the really cutting edge study of black holes, there is some kind of suggestion that a sort of wormhole might be present and might play a role in solving something called the black hole information paradox. So there's an idea that you can kind of, and I keep using these caveats because they're not, it's complicated, but you can sort of imagine the singularity in the black holes and network.
I remember one of your lecture about the information paradox, we can burn the book and the atoms left, and then we can reconnect atoms to recreate the books.
As far as we understand the laws of nature, then in principle, you could set fire to a book and you could burn it. And if you could perfectly collect everything, the light and the heat and the atom, everything that comes off the book, all the photons, all the bits of smoke, the lot, right? And you could measure it all perfectly. And in principle, you could reconstruct the book. So obviously in practice, you can't, but in principle, you can. Now, the wonderful argument triggered by Stephen Hawking's work initially in the 1970s about black holes is that true of a black hole? So if you throw the book into a black hole, then does the information somehow get stored? Does it ultimately get returned to the universe? Because black holes have a lifetime, we now know, so they ultimately evaporate away due to this process Stephen Hawking discovered called Hawking radiation. So ultimately the question is that information somehow imprinted in the Hawking radiation? When the black hole's gone and all there is this radiation that's been emitted from it. And initially, the great paradox was that initially Stephen Hawking's calculation said, no, it isn't in the radiation. The information is featureless, informationless. It will not contain information. So it meant that whatever goes in essentially gets not only completely scrambled up, but erased. That was the calculation, right? So, Stephen Hawking. Now, we've spent, by we, I mean, hundreds, thousands of physicists have spent 50 years trying to understand what actually happens. And the current consensus now is that the information comes out again. So ultimately, in a very scrambled sense, it is imprinted in the radiation. And so then you get really interesting questions like, well, how? Because the radiation that comes, first of all, Stephen Hawking's calculation said it doesn't, right? So there's something wrong with the calculation. And secondly, the way it's produced. The interesting thing about Hawking radiation is that how does it, you have to think, just to step back, a black hole in Einstein's theory is described as pure space-time, right? It's just space-time geometry. This radiation is coming from what's called the event horizon of the black hole, which is just space. So it's almost as if a way to think about it is the black hole is kind of shaking or tearing this radiation out of the vacuum of space. It's coming from the vacuum. It's not coming from the thing that fell in, right? So the question is, if something goes in and then this black hole disappears and all the radiation has come from something to do with the event horizon and the vacuum of space, how can it be that this thing that fell in gets imprinted in it? And that's where the recent calculations, I mean, very recent in the last few years, have suggested the information comes out. And then the way it comes out, this is active research. But as I mentioned earlier, one picture, which is very speculative, is that some kind of wormholes, some sort of wormholes, not the Einstein-Rosen bridges, by the way, some other kind of open up from the interior of the black hole to the exterior. And somehow the information comes out through wormholes. But that's very, very a speculative interpretation of some difficult mathematics. And there's no consensus on that. It's very exciting because what it's actually doing is it's showing us a glimpse of a deeper theory of space and time. That on that, I think most physicists agree. But what we're glimpsing, I don't think most physicists agree on.
Do you believe that we will ever connect quantum physics and classical physics?
Yes, I do. I mean, even now, there are several questions in there. One is just how quantum mechanics produces the world that we see, which doesn't appear to us to have quantum-like properties. Like things can't be in several places at once, for example. And we're beginning, I think, to get a good understanding of that. I think the consensus would be that the world is described at its base level by quantum theory. But another question, which we're also making progress on, is there's an idea called the holographic principle, which is related to the idea that you can represent space and time themselves as a quantum theory, an entangled quantum theory. It goes, but if you want to look things up on the web, there's something called ADS-CFT, which is a very famous conjecture theorem discovered by a physicist called Juan Maldacena a long time ago. And so there are windows, I think, into this possibility that, and I think most physicists in the area would agree with it. The base level of reality looks to me and virtually everybody else as like quantum mechanics, a quantum theory of some description. And out of that, the challenge is to decide, and we don't know how this works yet, as you said, to decide exactly how the reality that we perceive emerges from the deeper theory. But I'd be surprised. There are very few people now, I think, who think that the deep theory is not quantum mechanics. It's interesting that the study of the very, very precise questions in the study of black holes have are leading us down these interesting paths. That's one example. So the reason black holes are interesting, there's lots of reasons. They're interesting things, but one of them is you can pose very simple questions about how information behaves. It's quantum information. Questions about quantum entanglement, which we can also study. Of course, we're studying in laboratories around the world. So we're building quantum computers, which are also giving us a deeper insight into this theory and how it behaves in practice. So I think we're on the verge of a real leap in our understanding of what quantum theory is and what it implies for the way that the world works. And a quantum computer is a great example. I mean, these are real things. They're physical things that do things. We can program them to do useful things. You can go on the web and use a quantum computer as a subroutine in your computer program. But those things are operating purely according to the laws of quantum mechanics. And these ideas about, for example, quantum entanglement, which have been, if you go back a few decades were purely theoretical, are now experimental. And they're not only experimental, it's engineering now, because we're building systems, quantum computers that rely on it to work.